Think about this. Water sits quietly in a glass. Nothing dramatic, just liquid. Now lower the temperature slowly. Nothing changes. Still liquid. Lower it more. Still liquid. Then, at exactly 0 degrees Celsius, something extraordinary happens. It freezes. Not gradually, not partially, structurally. The same molecules, the same H2O, but the configuration reorganizes. Liquid becomes solid. This is a phase transition, and it may be one of the most important structural principles in physics. Because phase transitions explain something subtle about reality. Change is often invisible, until it isn't. For a long time, nothing appears to happen. Parameters shift quietly. Energy changes gradually. Pressure increases. Temperature drops. Then a threshold is crossed, and the system reorganizes. Suddenly. This is not metaphor. It is mathematical structure. In thermodynamics and statistical mechanics, a phase transition occurs when a system moves from one state to another due to a change in an external parameter. Temperature, pressure, magnetic field, interaction strength. Above 0 degrees, water molecules move freely. Below 0, they lock into crystalline order. The molecules do not change identity. Their relationships change. Structure reorganizes. Now consider magnetism. Above a critical temperature, atomic spins in a material are randomly oriented. The material is not magnetized. Lower the temperature below the Curie point. Suddenly, spins align. The system chooses a direction. Magnetization emerges. Before the threshold, randomness. After the threshold, structure. This threshold is called critical temperature. At the critical point, something remarkable happens. The system becomes highly sensitive to fluctuations. Small disturbances can have large effects. This is called criticality. Near critical points, systems become unstable, and instability allows reorganization. Physicists like Leo Kadanoff and Kenneth Wilson studied these phenomena deeply. Wilson's work on the renormalization group showed that behavior near phase transitions depends on scale. Zoom in and you see local fluctuations. Zoom out and you see large-scale patterns. Near criticality, small-scale fluctuations propagate across scales. The system becomes correlated across distances. Correlation length increases. In simple terms, at critical points, everything starts influencing everything. This is why water freezes suddenly. This is why magnets align. This is why superconductivity emerges. Now pause and think about something more abstract. Phase transitions are not limited to matter. They appear in ecosystems, in financial markets, in neural networks, in social systems. Complex systems often hover near criticality. Why? Because near critical points, systems are maximally adaptable. Too much stability, and the system becomes rigid. Too much instability, and it collapses. Near criticality, the system is balanced between order and chaos. It is sensitive but structured. This balance is powerful. Neuroscientists have proposed that the brain may operate near critical states. Why? Because critical systems maximize information processing and adaptability. Too much order, rigid thought. Too much chaos, incoherence. Near criticality, flexible intelligence. Now let's shift carefully. When you look at your own life, you often expect change to be linear. You think, if I improve 1% every day, I will feel 1% different every day. But complex systems do not behave linearly. Parameters can shift gradually without visible effect, until they reach a threshold. Then structure reorganizes. Think about habit formation. For weeks, you adjust sleep, information intake, physical activity. You feel little change. Then one day, your emotional baseline shifts. You respond differently. That is not magic. It is threshold crossing. Or think about burnout. Stress accumulates slowly. Everything seems manageable. Then suddenly, collapse. Not because collapse came from nowhere, but because a critical parameter was crossed. In physics, we can measure temperature precisely. In life, parameters are more complex, but structure still governs behavior. Phase transitions teach something essential. Stability can mask accumulated change. Because what matters is not incremental visible difference. It is proximity to threshold. And thresholds are nonlinear. Now let's go deeper into structure. At the microscopic level, water molecules are always moving. Even near freezing, local fluctuations exist. But only when enough molecules align cooperatively does a new phase stabilize. Cooperation across scale is key. In statistical mechanics, this is described through order parameters. An order parameter measures the degree of organization in a system. For magnetism, the order parameter is net magnetization. For water freezing, it is crystalline order. Above critical temperature, order parameter is 0. Below critical temperature, it becomes non-zero. Structure emerges. Now imagine psychological order parameters. Patterns of thought, emotional regulation stability, self-concept coherence. These can remain below threshold, fluctuating but not reorganized, until conditions shift enough to produce new stability. Phase transitions show that transformation is not additive, it is structural. Liquid does not become slightly solid, it becomes solid. A magnet does not become partially aligned gradually in linear fashion. It reorganizes cooperatively. Transformation involves coordination across parts. This is why superficial change often fails. Changing one parameter slightly may not push the system past criticality. Change multiple reinforcing parameters, and the system reorganizes. This is why context matters. Water freezes only when temperature crosses threshold. Lower pressure changes threshold. External conditions determine critical points. Likewise, environment influences human thresholds. Sleep, stress, relationships, information diet, physical state, these are interacting variables. No single variable guarantees transformation, but coordinated shift can. Phase transitions also explain something else. Sudden growth. Sometimes people appear to overnight succeed, but underneath, parameters shifted slowly. Skill accumulation, network building, learning, then threshold, visibility, recognition, structural shift. The visible moment is the phase transition. The invisible period was parameter adjustment. Physics shows that invisible buildup precedes visible change. This reframes impatience, because if you judge progress only by visible structure, you miss proximity to threshold. In water, temperature can drop from 10 degrees to 1 degrees with no visible difference. But you are 1 degree away from structural reorganization. Now consider something even more subtle. At critical points, systems become scale invariant. Patterns repeat across scales. Small fluctuations resemble large fluctuations. This is called fractal behavior. In this state, systems are exquisitely sensitive. Small input can reorganize entire structure. This sensitivity is powerful but dangerous. Near criticality, slight perturbations can cascade. Avalanches and sandpile models occur this way. Financial crashes can reflect this. Ecological collapse can reflect this. Critical systems are creative but unstable. So balance matters. Too far from threshold. Stagnation. Too close. Volatility. Now let's return to something personal. You may fear instability. You may interpret emotional fluctuation as regression. But physics shows that instability often precedes reorganization. When structure destabilizes, it signals parameter shift. The question is not how to eliminate instability. It is how to regulate parameters. Water does not freeze randomly. It freezes under temperature constraints. Structure follows law. This is where discipline matters. Not discipline as force, but discipline as parameter management. Sleep stabilizes neural systems. Information diet stabilizes cognitive priors. Physical regulation stabilizes mood. These are thermodynamic variables of human systems. When enough parameters align, phase shifts occur. And when they occur, they feel sudden. But they are lawful. Phase transitions are not miracles. They are structural inevitabilities under condition change. The universe reorganizes not through chaos, but through threshold crossing. When a system approaches a critical point, something remarkable happens. Its behavior becomes less predictable locally, but more coherent globally. This sounds contradictory, but it isn't. Far from criticality, systems are stable but rigid. Perturbations fade quickly. Drop a pebble into warm water and the ripples dissolve almost immediately. The system absorbs disturbance without reorganization. Far beyond criticality, systems are chaotic. Perturbations amplify uncontrollably. There is no stable pattern to return to. But near criticality, at the edge between order and disorder, systems exhibit what physicists call long-range correlations. This means parts of the system that were previously independent begin to move together. In magnets near the Curie temperature, atomic spins become correlated over long distances. In fluids near boiling, density fluctuations occur across scales. In neural networks near critical states, firing patterns synchronize dynamically. At criticality, the system is most responsive, most adaptable, most capable of reorganizing. This has profound implications. Because adaptability is not maximal in perfect stability, it is maximal at the edge of transition. Now consider entropy again. Entropy increases globally in closed systems. But locally, order can emerge when energy flows through the system. A star forms because gravity concentrates matter. A cell organizes because energy gradients drive chemical reactions. A brain organizes because metabolic energy sustains neural firing patterns. Order is not opposed to entropy. It exists within entropy. Living systems are dissipative structures, a term popularized by Ilya Prigogine. A dissipative structure maintains order by exchanging energy with its environment. It remains stable by not being closed. If energy flow stops, structure collapses. This is true in physics. It is true in biology. It is true in identity. You remain stable not because you are rigid, but because you exchange information and energy continuously. Now, let's bring this to transformation. When people attempt change, they often focus on outcomes rather than parameters. They try to become disciplined, but discipline is not a switch. It is emergent from parameter alignment. Sleep affects impulse control. Nutrition affects energy regulation. Information exposure affects cognitive bias. Social environment affects reinforcement loops. When enough parameters shift, a new stable pattern can emerge. Until then, efforts feel inconsistent. Water cannot freeze if temperature hovers above threshold. No amount of wishing changes phase. The variable must change. This reframes frustration. Because visible change lags parameter adjustment, and critical thresholds are nonlinear. At 1 degree above freezing, water looks identical to water at 20 degrees. But structurally, it is close to transformation. The difference between stagnation and reorganization may be smaller than it appears. Now consider instability. Near critical points, fluctuations increase. The system looks noisy, uncertain. In life, moments before transformation often feel chaotic. Habits feel fragile. Emotions fluctuate. Identity feels unsettled. But this may signal proximity to threshold. In physics, before water freezes, microscopic clusters of crystalline structure form and dissolve rapidly. They appear and disappear. Then suddenly one cluster stabilizes and propagates. The phase changes. Those temporary clusters are precursors. Likewise, small experiments in behavior may appear unstable before stabilizing into new patterns. Temporary instability is not regression. It is precursor fluctuation. Now think about scale. Kenneth Wilson's work showed that near critical points, systems become scale invariant. Patterns look similar, whether you zoom in or out. Small fluctuations resemble large ones. This suggests that transformation may not require massive intervention. At the right scale and threshold, small adjustments can propagate widely. But timing matters. Small change far from threshold has little effect. Small change near threshold can reorganize everything. This is leverage. Leverage is not force. It is alignment with system sensitivity. In sandpile models, used in complexity science, grains of sand accumulate gradually. Nothing dramatic happens. Then one grain triggers an avalanche. The avalanche was not caused by that grain alone. It was caused by accumulated structure reaching criticality. The final grain was a trigger, not the cause. In life, visible transformation often appears triggered by one event: a conversation, a decision, a moment. But that moment reflects accumulated parameter shifts. Now let's talk about fear. Humans prefer linear progress. Linear progress feels safe, predictable. But complex systems are rarely linear. They are nonlinear and threshold dependent. Understanding this removes unrealistic expectations. You may work steadily with little visible shift, then experience structural reorganization. Or you may accumulate stress invisibly until collapse. Both follow similar structural logic. So the deeper question becomes, how do you regulate proximity to criticality? Too far from threshold, rigidity. Too close, volatility. Living systems often function near but not beyond critical points. The brain, for example, appears to balance excitation and inhibition carefully. Too much excitation, seizures. Too much inhibition, coma-like suppression. Near balance, adaptive cognition. Balance does not mean perfect symmetry. It means dynamic tension. Now consider identity again. If identity is stabilized configuration, then growth may require temporary destabilization. But destabilization without regulation leads to collapse. Regulated destabilization leads to reorganization. In physics, cooling water slowly allows controlled freezing. Rapid, uncontrolled cooling may cause fracturing. Parameter management determines outcome. This is structural maturity, not dramatic force, not suppression of fluctuation, but intelligent modulation of variables. Now return to the beginning. Water freezes suddenly, but only after invisible shifts. Magnets align abruptly, but only after thermal fluctuation drops below threshold. Superconductivity emerges dramatically, but only under precise conditions. Phase transitions reveal that change is not gradual at the level of structure. It is gradual at the level of parameters. Structure changes at threshold. If you misinterpret gradual parameter adjustment as failure, you quit before reaching criticality. If you misinterpret instability as collapse, you retreat before reorganization. Physics teaches patience, but not passivity. Patience in parameter alignment. Precision in environmental variables. Respect for law. The universe does not transform randomly. It transforms when constraints and energy conditions cross boundaries. This makes transformation less mystical, less emotional, more structural. You do not need to reinvent yourself from nothing. You need to understand which variables control your configuration. Change those consistently. Allow instability without panic. Watch for clustering, early signs of new pattern stabilization. Then threshold arrives, and what looked impossible becomes natural.